Welcome. We are looking at variational calculus. Specifically, we looked at functionals. Functionals are functions of functions. An example is the action functional, which is used in classical mechanics, in which we found that the kinetic energy minus potential energy, which is defined as the action for the particle at every point, at every instant of time. For example, the particle has a position, at that position it can have any velocity. So, positions as well as velocities become independent variables and with respect to time, and so we could write a functional, and in such quantities we were looking at the equivalent of the condition in the case of a single valued function like f of x is equal to 0, some polynomial in x. Then we know how to look at the extrema points for this polynomial. We take the first derivative, we equate it to 0, we take those solutions, we put it in the second derivative, we look at the sign, and then we decide whether it is a minima or maxima. In a similar fashion, you can define the first variation for functionals, which is what we derived and which goes something like this. So, we defined the functional I as an integral f x y prime, which is nothing but dy by dx integrated over dx from point x1 to x2. So, this is what we defined, and in this case we said that the Euler-Lagrange equation, which is the first variation. So, that we said is nothing but dou f by dou x minus d by dx of dou f by dou y prime is equal to 0. This is how we define the Euler-Lagrange equation. So, this is for the first variation. Okay. In this case, now we want to consider the action principle. So, let us define the action as this quantity, goes from some t1 to t2, and we said that it is t minus v dt. The principle of minimum action says that where t is the kinetic energy, so it is given as half m x dot squared, and v is the potential energy, and it is just a function of x. Now, given these two, now if we are trying to optimize this function, so this function can now be written, if we want to write it in this form, as this. So, sum f of t x and x dot, which is nothing but dx by dt. So, this is what we have integrated over dt. So, we can use for this functional now the Euler-Lagrange equation, and we can try to write it. So, if we write it, then we will see what happens. Okay. So, the principle states that this action should be minimized, and where this f is nothing but half m x dot squared minus v of x. If we want to minimize this functional, then we know that minimization means the Euler-Lagrange equation. In this case, because t happens to be the independent variable, the Euler-Lagrange equation would be this x minus d of if we take this functional and if we do this, so this should be equal to 0, this is the Euler-Lagrange equation. So, dou this functional by dou x, then you see that this is the only explicit function of x. So, you have minus dou v by dou x, v which is a function of x, minus d by dt of dou f by dou x dot. So, if we see this is the only term which has x dot. So, if you assume that m is a constant, now 2 and 2 goes off. So, you get m x dot is equal to 0. So, if we now take this, that leads to the following expression. So, we get minus dou v x by dou x minus, again m is not changing with time. If you take that, then you have m x double dot is equal to 0. In other words, if we know that the negative gradient of the potential is nothing but the force is equal to m x double dot. This is the Newton's equation. So, we find that the classical action principle, so you can define a functional called action, and that is nothing but integral between time t1 to t2, the kinetic energy minus potential energy integrated over time, and we say that now we want to extremize this functional, and we use the Euler-Lagrange equation because that is the necessary condition. So, Euler-Lagrange equation is like making the first derivative of a function equal to 0 and getting the solutions to find out where the extrema are. So, if we do the same thing with this functional now, we obtain Newton's law, F equal to mass times acceleration, and this came from minimizing the action which was defined as t. So, there is a nice description of this functional and the so called action principle in Feynman's lectures on physics. So, you can take a look at it. So, this is an example of how the functional is written, how Euler-Lagrange equations are used and what they give us. So, you can see that this is a nice elegant principle solving which basically we attain Newton's laws. So, classical particles will obey Newton's equation, but because Newton's equation is obtained as an minimization over this functional called action. So, minimization of action is basically the principle from which you can get the Newton's laws. So, this is a way of looking at classical dynamics. So, it demands that minimization of the action is basically equivalent to solving the Newton's equation. Okay. So, this is an example. So, in the next part of this lecture, we will go take a closer look at what is this variation, and there is a formalism known as delta operator formalism, which makes this process of taking variational derivative a little bit more methodical and hence mechanical. So, we will look at those two aspects in the next part of this lecture. Thank you.